PFAS are everywhere. These chemicals have been used for decades. Products that we use in our daily life, even in applications that are critical, like medical devices.
All of these are man-made substances. They're not found naturally.
And that's why they call them the forever chemicals. So they're used in so many different processes.
This is a chemical that doesn't really break down very easily, and it seems to bioaccumulate in animals and plants and people.
The most recent interest in this is really driven by the potential that these compounds might be regulated in drinking water.
We're all trying to understand the totality of the PFASs that are in our world and what form they take. How many PFASs are out there is that grand challenge right now.
PFAS have been around since the 1940s. That's really when we started using them. But the reason we started using them was because we thought these were very inert compounds, right? So they kind of stuck around for a long time. Well, what we started to learn now is they stick around for a long time, so they don't break down and they're present in the environment.
Now we are finding that it's in every single person on this planet and in all sorts of fish, wildlife, and plants. So that's causing an alarm, and especially for chemicals that do not break down. Why it took so long for us to figure out that it was a concern was because the effects that these chemicals have on biology are very subtle. So things like cancer take a while, like a lifetime, to show up in organisms. And so to attribute all of these chemicals to those types of diseases, it's hard. And it's only until now where they've been able to gather enough epidemiological evidence to sort of connect disease clusters to these contaminants.
Only recently we are more interested in the regulations of PFAS, and that's partly because how it was regulated in the past. Manufacturers were not required to report the use of PFAS in the consumer products that they were producing, and hence there were no testing required for PFAS in the environment and in the products.
In the United States, the EPA monitored for the first time PFAS in drinking water. This was completed in 2016. Shortly after that, the general media published the results about the presence of PFAS in drinking water. Around that time also, it was published that Genex, a new PFAS, was in drinking water, even though scientists had discovered it in 2012. All this happened around the time of the Flint water crisis, and that drove public interest into water quality. Then the regulatory activity accelerated because of this public concern, and that brings us to the present when there is lots of work happening from different stakeholders.
I think if you look at social media today, it gets the information out there really quickly. So the research is being done, that's being tweeted out there through Twitter X, also through Facebook, through LinkedIn. So there's a lot of researchers that actually publish their work in these avenues. And then you see a lot of people picking it up and responding to that research work.
We know they're certainly in the news recently, and we have movies like Dark Waters and The Devil We Know. We also have a book that's in the popular press by Rob Balot that document contamination of communities by PFASs.
As time has progressed and more testing has been done, that greater amount of data then generates greater public knowledge. That greater public knowledge then pushes regulatory agencies for more testing and public health research. That greater amount of research then pushes for more further testing, and it just sort of builds up on itself. We've hit kind of a critical mass at this point where PFAS testing is now the big hot topic for environmental contamination.
PFAS, the whole compound class, has a lot of valuable properties. That carbon-fluorine bond makes it very valuable to industry. Unfortunately, it also makes it very resistant to degradation. You might get them from food packaging, microwave popcorn is a big one. Another large source is the use of aqueous film-forming foam in firefighting, fuel-based fires, which is in particular done at airports and Air Force bases. These foams are basically a complex mixture of fluorinated compounds that then can lead out historically into the environment, and that's a big source of them.
If you have a military base or if you have a firefighting facility that has repeatedly practiced putting out fires, we now know that that increases the risk in a watershed for contaminated water. After that, if you don't live in one of those watersheds, it's most likely that your PFAS source is through the food supply. When you start moving away from those known sources, we can start to look around us in our own personal worlds, at home, schools, businesses, even automobiles. Papers and textiles have been treated for water repellency, but also oil repellency. We have PFASs in indoor and outdoor paints, paints that are put down on roads. And so those PFASs can be in runoff, in stormwater. We're still learning about where to find PFASs, but those are some common ones.
Because of how robust these chemistries are to break down, we know that they can actually spend years traveling through the environment and migrate quite a long distance, miles, hundreds of miles from where they originally started.
We have direct and indirect ways to look at PFAS. So there are indirect methods that give us an idea of the total amount of fluorine that is on a material or in an environmental sample. But then there are these individual techniques that many labs are engaged in. These specific tools help us sort of color in that total fluorine space, help us understand what we know and what we don't know.
So the types of instrumentation that are really critical to understanding PFAS really starts with instruments that are made for detecting PFAS. For targeted PFAS analysis, the gold standard is liquid chromatography with tandem mass spectrometry. There is a greater push for gas chromatography with tandem mass spectrometry as more volatile PFAS become of interest, but those two techniques are really the key for understanding the presence of PFAS.
For screening methods, a single quadrupole is a very good instrument actually, because you're able to do remediation or QC checks. With a less expensive instrument, you're able to find out whether or not PFAS are present. If you do get a hit, then you can go to a more sensitive instrument such as the triple quad to then vet those analytes that have a hit.
There are so many different PFAS around that a targeted approach can't catch everything. So non-targeted using high-resolution mass spectrometry is also widely used to identify and characterize PFAS. To further simplify things, a technique called adsorbable organic fluorine can then be used to quantitate a total fluorine amount, which then can be related to a total PFAS exposure potentially.
The use of combustion ion chromatography. And this is a technique that screens for the total organic fluorine concentration. We know PFAS compounds contain significant amount of fluorine, so this screen captures the baseline or the aggregate amount of potential PFAS and other fluorinated compounds such as pesticides.
How many PFASs are out there and what makes up that total fluorine is that super grand challenge right now. And we're lucky that the stable of instrumentation is expanding to help us go specifically after that question and really try to illuminate which PFASs have we been missing thus far, and when do we reach a complete and total understanding?
To this point, we don't even know the exact number of PFAS that are out in the environment. Some people say it could be 1,000, some say over 5,000, some people say as many as 1 million. We constantly see evolving and newer regulations, right? That means testing for new PFAS, testing for new levels. So you constantly have to stay up to date and create new analytical methods to capture all of those.
And we've seen a lot of work in method development, especially from regulatory agencies. But also having dedicated and good equipment and consumables is very important for PFAS analysis. Since these are used heavily in industry and manufacturing, they can kind of creep in to any tools that you're using in the lab to measure them. So it's critical that anything that you use in the lab to do these measurements doesn't add PFAS to your sample as you're handling it. So that would be creating like a false positive. Another thing would be a false negative, so you don't want anything to absorb or retain any of that PFAS when you're handling, because that would result in a false negative.
As you go to lower and lower targeted levels, that's definitely something you need to optimize. As the compound list expands, that can be important, is to develop new methods to encompass the different chemistries that are involved in the PFAS class. So that is an important aspect of doing PFAS analysis.
As instrumentation gets more sensitive, that becomes even more of an issue, just being constantly vigilant about looking at our solvents, our waters, our tubes, containers, just keeping track of that. Just turns out to be one of those day-to-day challenges that we all face. With some of those tools, for example, the high-resolution instruments, they generate huge quantities of data. And one of the big challenges is actually extracting all the usable information out of those files. And so all labs engaged in this type of analysis, either now or in the future, will have to take on advanced statistics and machine learning tools to really extract the maximum amount of information.
So PFAS are regulated at very low levels, in parts per trillion levels, and like the MCL goals are zero, essentially. And the health advisory level that was given by the US EPA was in parts per quadrillion level. So one of the biggest challenges is getting the instrument to detect such low levels of PFAS in water samples.
So if we take an example of regulation, say in water, typically we're looking at PFAS at the low nanogram per liter level. So what does that mean even, right? A low nanogram per liter, so let's say like an example of 1 nanogram per liter, is pretty much the equivalent of 1 drop of water in around 20 Olympic-sized swimming pools. So this is an extremely low level that we are having to measure PFAS.
The drinking water industry was really a primary target initially because if you think about it, we're exposed to water every day, right? So whether you're using it for cooking, you're drinking it for any types of processes. So making sure that the drinking water is safe. And then if you look at the sources of contaminants, landfills. So when you dispose of these materials, they leach into the water supply. And so if somebody is on for example, a well water, there's a potential that can leach into their well water. If you look at just disposing of materials, it could get into, let's say, a reservoir, and so contaminate the reservoir. So the drinking water is really important because we're exposed to water every day.
In the US, we know that the Clean Water Act, or CWA, is a federal law in the United States that was enacted in 1972 with a purpose to protect and restore the quality of the United States waters, including rivers, lakes, streams, wetlands, and coastal areas. And the CWA sets standards for water quality, including drinking water. For PFAS testing specifically, drinking water has been a focus due to the prevalence of this compound across the US. And we've seen the regulations evolve over the last handful of years to include more and more compounds in those lists. Initially, the EPA started with the regulations of 18 and 25 PFAS compounds with their methods 537.1 and 533 respectively. But as more compounds are being attributed to be a health concern, we've seen that list increase. And now the most recent list from the EPA for drinking water is up to 40 PFAS compounds. And more details can be seen in method 1633 that show the workflows and the protocols needed to test for this accurately.
There are some misunderstandings when a method is approved by EPA. That EPA approves an analytical method doesn't make it a regulation. The methods support future rulemaking. So 1633 is the latest method that EPA approved for the analysis of PFAS in wastewater samples, solids, biosolids, tissue, and it's an excellent tool for labs to be able to compare apples to apples. Now we have a standard method that tells us how to process the samples, how to quantify PFAS, and more importantly, we have quality control criteria that we need to demonstrate we achieve to make sure that the results that we are generating for PFAS are good. EPA is working on the future regulation of wastewater biosolids. So when that rulemaking happens under the Clean Water Act, EPA 1633 will be the tool for labs to provide results about the PFAS concentration to support that regulation.
So the new method 1633 released by the EPA changes the landscape of PFAS testing because it opens up matrices that currently weren't covered by existing EPA methods. Prior to the release of this method, the Department of Defense had their quality service manual, which outlined some testing for non-drinking water matrices involving solid phase extraction and carbon cleanup. But at the time, there was no EPA method that directly targeted that. People were running modified drinking water methods to meet this requirement. Once the EPA released a draft form of this method, which did cover this use case, labs immediately jumped on it even before it was finalized, which showed that there was really a lack of that specific application that was really needed for the market. How this is really going to change how labs look at things, it's really going to put more of a focus on sample prep. Previous drinking water methods were with very friendly samples where sample prep was necessary but not necessarily terribly difficult. As you get into wastewater and solids and biosolids, a robust sample prep and a robust cleanup will be really required by the labs to keep their instruments up and running.
I think there's a lot of nuance involved in terms of how you deal with source characterization and who are potential emitters. What I will say is, again, the EPA, I think, is taking an active role in this, working directly with a lot of industry and manufacturers. They've added in a couple of pretty important pieces of legislation. One is around the toxic release inventory, or the TRI, under what we call the TSCA Act, and that really means any industry using over 100 pounds of PFAS annually is responsible for reporting that to the US EPA. And so this is an important first step because it'll kind of give us an idea of who the users of PFAS are and potentially then where to look for PFAS contamination in the environment.
I would expect in the future you'll see regulations around food packaging because there's a lot of PFAS materials used in food packaging. There was an interesting piece done, and I think most people are not aware, but dental floss is an example, right? The smoothest of the dental floss comes from the PFAS materials that are in the dental floss for some brands. And then also, obviously, they're looking to come up with non-PFAS related firefighting foam agents so that they can move away from that. And then also, they're looking at non-stick alternatives because PFAS is used in non-stick cookware. And so now you're seeing a lot more companies advertise that they're PFAS free. So when you're buying the cookware that says non-stick, you know that it's PFAS free. So I suspect we'll see more and more regulations around those consumer goods and packaging materials.
There is now a big interest in closing the mass balance. So when we've been looking, at targeted techniques, that's only a fraction of the PFAS compounds that are out in the environment. Most of the historical PFAS research or quantitation has been done with LC triple quad, which is a targeted analysis technique. So it depends on you knowing what you should be looking for. So I'd say recently there's been a larger interest in non-targeted MS, which allows you to look at unknown identifications. But going with that is the use of the new proposed method, EPA 1621, which is a total adsorbable organic fluorine method. So that's just looking at trying to capture all the organic fluorine in the method. And when they try and close this mass balance between the targeted techniques, the non-targeted, and EPA 1621, then that's where you see that there's still a lot of research to be done to find out what the most important fluorinated compounds in the environment are, because there's still a lot out there.
So there are some positive advancements in the field of PFAS, and I think many researchers are now focusing on the destructive treatment of PFAS. So we realize PFAS are very resistant to degradation. So research focusing on breaking down those carbon-fluorine bonds in PFAS is very promising, and there are many approaches that shows promise in completely defluorinating PFAS in environmental matrices. And also, it's encouraging to see more and more interdisciplinary research in the PFAS area. So you have researchers like from physics and chemistry and biomedical and computer science engineering contributing to PFAS research who have completely very different perspective on the contamination issue of PFAS. I think their contribution is critical in addressing this global issue.
As we know, more and more samples will be coming into these labs. The use of sample preparation automation platforms is going to be critical. So understanding the options available today and how they'll support one of the mass spectrometry workflows is becoming a very popular topic. So working with the provider that can really provide that comprehensive workflow, I think will put someone in good standing for future-proofing their lab.
The ways that we've been approaching toxicity and harmful effects in the past usually look at one single chemical at a time. When you have a whole mixture of these compounds that you're exposed to, you will not be able to figure out the effect of one chemical from all of these other chemicals. We're developing all these suites of assays that are run by robots, essentially. And then we run these chemicals or these mixtures of chemicals through these robots and see if there's anything there that's going to be harmful to life. And then if we do, then we go back and figure out what the chemistry is. How we've been approaching it right now is we have the chemistry and see how the biology responds. But I think now we're starting to shift towards okay, we have the biology, now let's figure that out, what the chemistry that's causing that, and deal with it that way.
Currently, PFAS laboratories tend to be overwhelmed with samples, turnaround times are slow, capacity is at maximum. A direct-to-MS technique that simplifies sample prep and bypasses chromatography can definitely increase the capacity of the labs, getting more samples out and helping to improve everyone's knowledge of PFAS exposure much more quickly. On the waste side, current waste destruction techniques such as incineration can't fully break down PFAS compounds. If you incinerate PFAS waste, you're turning large chain PFAS compounds into a number of shorter chain PFAS compounds and then usually emitting these out into the air. There are numerous companies that I've talked to that are working on alternative destruction techniques that can fully break down the PFAS so that waste destruction doesn't just create more PFAS into the environment.
I think that there have been advancements throughout the entire laboratory. In terms of sensitivity, we're getting down to the part per trillion level, single digits. That's remarkable considering how low of a level that is. And we predict that those levels will continue to become more and more sensitive as new regulations and new methods come out from regulatory agencies. In terms of the matrices, whether that be a solid, liquid, air, or even tissue, we have instruments that are able to extract things from these matrices or even analyze the matrices themselves. It's incredible to see what analytical instrumentation is able to do in our current age. I'd like to touch on high resolution because a high resolution mass spectrometer is amazing in that you can identify truly unknown unknowns from a matrix, and then we're able to determine the unknowns of not just PFAS but the universe with these advanced mass spectrometers that we have, and I find that truly amazing, and it's really helping us to determine not only how to address issues like PFAS but other environmental and public health concerns.
We see people taking these analytical tools and really helping understand where these materials occur, where the PFAS occur in commerce, and help guide selection if you want to avoid, or in some cases we might not be able to avoid them based on the special properties that PFAS impart to, say, materials, for example, like fluoropolymers. Looking at the consumer products like paints in your indoor environment that can inform exposure, occupational or, say, home occupant exposure. That's an important development. We see analytical instrumentation getting more sensitive, and also ones designed to do surface analysis. For sure, the high-resolution mass spectrometry is here to stay. That is a trend where I think you'll see adoption and movement into the contract laboratory environment. Also, those advanced workflows, that ability to deal with the information from a statistical perspective, those are all trends that are going in the right direction, moving into increasing number of environments out of the academic lab and moving into the larger scale production lab.
I think for labs to be more successful or productive in testing for PFAS now and into the future is really to invest in making sure they're staying on top of the regulations that are going to be forthcoming, attending those conferences where they're talking about the regulatory actions that are taking place or proposed actions that are taking place. And then also making sure that the laboratory professionals are staying up to date on the latest technologies so that they can make sure that when those new regulations go into effect, they're actually ready for doing the tests in-house. So I think it's a combination of staying informed and really making sure that the laboratory personnel are being educated and trained to the highest level for doing these analyses.
By working together, we can address the challenges from upcoming regulation, and what I think is also very important, inform the legislators to make sure that the regulation incorporates the latest science.